Hello. Um, Today I'm going to be talking about continuous random variables. So the fourth lecture series will be about continuous random variables. It's going to be a continuation from discrete random variables. If you recall, discrete random variables corresponded to two series. One of them is a finite series, like Bernoulli distribution, which consists of only two terms, 0 and 1, two elements. It consists, for instance, uniform discrete random variable, which consists of the integers between a and b, and you can divide them as one by one or any other way, but it's going to consist of a finite number of terms, or binomial distribution, where you have n different elements, which is going to go from n plus 1 elements, where n correspond to number of trials. You may have 0 success, 1 success, 2 up to n successes. And you can also, we saw countably infinite series, which may be described as discrete random variables, like geometric random variable, which starts from 1 to goes plus infinity. So it consists of all the positive integers. And also we saw Poisson distribution, Poisson random variable, which actually corresponds to all the non-negative integers, and it is actually a countably finite, which comprise a countably finite series going from 0, 1 to infinity. Today we're going to continue with continuous random variables. So basically they are going to correspond to series which are uncountably infinite. So compared to countably infinite, these are going to be uncountably infinite. The typical example in mathematics is a real number. So anything, any physical quantity that is usually represented by real numbers actually corresponds to a continuous random variable. The typical examples are concentration, temperature, pressure. Actually, most of the process, what we call process variable in chemical engineering, corresponds to continuous random variables. We may very briefly, actually, when we are talking about chemical engineering, which we have not up to this point, but maybe from this point on, we may talk about a couple of examples or relations with chemical engineering. What we call process variables, what is measured during process, are usually comprised of or usually consist of continuous random variables, as I said. But on the other hand, we have discrete random variables. They are usually related to quality control. For instance, number of faulty products is a discrete random variable. But for instance, you measure the temperature of some product, or I don't know, a certain operation during some time. The time interval, it's going to be a continuous random variable. So also from this point, or maybe in other lectures, when a new variable is suggested to you in any other course, heat transfer, I don't know, mass transfer, think about what kind of a random variable, it may be in a real industry. All right, so we have, as I said, continuous random variables and probability distributions. A continuous random is random variable with an interval either or infinite or finite. Here it should have said actually finite or infinite of real numbers for its range. For instance, if you are talking about mole fraction between 0 and 1, note that since mole fraction, let's call it with x. When I say x, I'm not referring to x in our probability course, but the x that you have usually shown, the mole fraction within material and energy balances course, for instance. This is going to be a real number between, actually, we should write it 0 and 1. A real number, although this is actually within a finite interval, actually there is an uncountably infinite number of elements here. Therefore, this is going to be shown with a continuous random variable and continuous distribution. Whereas an infinite random variable may be, for instance, temperature. It may be from 0 Kelvin to, well, actually physically, as far as I know, I'm not good with physics actually, but there is a theoretical upper limit for temperature as far as I know. So maybe we should change this to some other variable, but for practical purposes you can take it as infinity. Therefore this is going to be an unbounded continuous random variable. Anyway, all right, so when we have continuous random variables, what's the big deal, you may say? The big deal is we don't have these spikes right now, because everywhere here x may take different values. So compare it to Poisson distribution. Although it may, Poisson distribution random variable also starts with 0 and goes to infinity, it occurs at discrete values. So Poisson random variable may 2, 3, 4, 5, all these values. But when it comes to continuous random variables, however you divide this interval smaller components, you are going to have always another value that is accessible to that probability distribution. So therefore, just like probability mass function giving each discrete value a spike like probability mass function such as this one will not work here. So what we do is, again referring to physics, what we are dealing with right now is going to be called probability density function. Compare it with probability mass function that we have used in discrete distributions, because here each point has a corresponding mass here, here, and here. On the other hand, here actually we are not going to be in continuous random variables. We are not going to be talking about single points. We cannot do that because of the reasoning I said. So therefore, we are going to be talking about density here. This is going to be converted mass. Therefore, probability using integration for a finite interval. So if you take, for instance, a metal rod such as this one, think about like this, then we are not going to, in physics, we do not talk about each point here each mass suspended from a single point here. There's going to be a continuous density spread over all the x direction. Let's say that this is only one-dimensional rod. It doesn't have a thickness in this direction and in this direction, so it is only in one direction. Therefore, when we want to convert the whole density quantity to mass, then what we do in physics is, there's going to be a density given here. Note that density is actually, you may think about mass in an infinite small dx region. So what we would like to do is, for a delta x, which is now a finite region value, if we would like to find a mass here, what we would do is we integrate this density value over this delta x. Then therefore we find the corresponding mass value. And the same rationale will be applied here. This time, instead of density in terms of kilogram per meter or meter cube kind of thing, whatever, this time we are going to have probability per some dimension. So it's going to be, let's say, an x value we are interested in, x random variable, and that small lowercase x corresponds to the values that it takes. So actually this is going to be what we call now small f is going to correspond to probability density function. At each point we are going to have a non-negative probability density function. But when it comes to finding the probability, just like finding the probability, it's finding the mass in this physical system, and since each point will not have a mass, but actually an interval is going to have a mass, the same rationale is applied here. There's going to be a non-zero probability if, okay, of course, this is the domain of the random variable x. There's going to be a non-zero probability between a and b, and we are going to be a probability of x between a and b. So that is a very important, interesting distinction, because in discrete random variables, fx is equal to probability of x being to lowercase x. Here in a continuous random variables, this is not going to be the case. Fx will correspond to probability density function. When we integrate it over some interval, we are going to be finding the probability that x value is going to be between a lower and upper limit. And single points here, just like in the physical analogy, single points. For instance, if I ask what is the probability at this value, you are not going to say that this is the probability, just like here actually this is the density. To have a finite probability, this density should be integrated over a region. Therefore, probability at a single point, whether you believe it or not, let's call it a single point, let's call it C, this single point here. Probability at x is equal to C if x is a continuous random variable. This is going to be equal to 0. Just like mass at a single point is equal to 0, because at each point there is density, but not mass. Mass is created when you integrate over a region. So the probability density function of x, what we call fx, consists of these properties. Now, just like probability mass function of a discrete system, at each point, probability density function should be greater than 0. You may again think about the physics analogy. There is no negative density, because when you integrate over all regions, right, any region over any region, you should have a non-negative mass value. It may be 0, it may be greater than 0, but it should be non-negative. Therefore, probability density function, just like probability, therefore probability density function should be non-negative over all the real axes. And probability mass function integrated between -infinity and +infinity is going to be equal to 0. You may also think about that, this integration over all domain of x or support of x. So when we integrate f over the domain or support of x, we are going to be obtaining the probability. And this is exactly what is suggested by the third property. If you would like to convert this density to probability, you integrate it over region A to B, and in this case, the probability will be equal to probability of x equal less than A, greater less than A, greater equal than A, and less than equal to B. So this is how you can convert probability density function to probability mass function. All right, a couple of more points. Let's get rid of these things I have written. Actually, there is an easier way if I push some button here. I think this one, nope. There should be this one, nope. I'm not still comfortable with those shortcuts. This, nope. Yes, I found it. Anyway, so note that what we call histogram in the very first chapter we talked about, in the very first lectures in descriptive statistics. Now what we show here and what we show as a histogram. Of course, histogram is a representation of a sample. This, on the other hand, is a representation of the distribution. On the other hand, you should realize that histogram is a discrete approximation of a probability density function. So if you take an infinite number of elements, this is from that distribution, this is what you are going to obtain as a histogram. I may put it that way. However, for finite samples, of course, this is going to be a more coarse-grained approximation. But as the number of sample size increases, you are going to be closer to the probability density function. And another point here is that for a continuous random variable, as I said, probability of x at a single value of x is equal to 0, which makes continuing from this third property, maybe you have thought about that when I try to pronounce this less than equal to thing, you can actually drop equal to a notation at any point, at any combination here. So these may be only less than x2 or only greater than x1 or both greater than and less than x1 and x2, because as I said, at the specific point of lowercase x, we have 0 probability. All right, Now, just like the discrete case, we have also cumulative distribution function. And from now on, there's going to be a very nice similarity between discrete random variables and continuous random variables. In discrete random variables, this was our actual, the most applied operation, summation. When it comes to finding the probability of a couple of events, we sum these values. When it comes to probability density function, I'm sorry, cumulative distribution function, cumulative probability function, then what we have done is we have added the probabilities, actual probability mass function of different values. And the same thing is applied here, but the only difference is summation is changed into an integration, which should make sense because now we are talking about continuous random variables. All right, so let's see the definition. Cumulative distribution function of x. What's the definition of that? The identical definition to that we have used in probability, discrete probability, or discrete random variables. It is probability of x smaller equal to lowercase x value. This is going to be an integral from minus infinity or the lowest value of x, which has a non-zero support, to the specific x value that we are interested in here. This is that lowercase specific value. If you take this integral, you are going to be obtaining probability of x being smaller than that x value. Note that you can also write this as 1 minus from x to plus infinity fx dx. Why? Because actually this one and this quantity will correspond to two mutually exclusive events. This is going to correspond to probability x smaller equals, and this is going to correspond to probability greater than x. And when you add these two, if you recall from actually, and this actually, not only they are mutually exclusive, but also they, when you take the union of those two, this is going to correspond to the whole sample space. Recall Kolmogorov's axioms, and the probability of sample space is going to be equal to 1. Therefore, when you add those two, since they are going to be equal to 1, if you just write this and put this, and if you put it here, and if you subtract this quantity from 1, then you obtain probability of x smaller than 1. So our probability density function, cumulative distribution function, is going to look like this. So if our probability density function is something like, I don't know, maybe, yes, something like this, let's say. Then the cumulative probability, the cumulative distribution function is going to be integral of this. So up to this point, it's going to be 0. From this point on, it's going to start increasing, and I couldn't show it clearly. I'm going to do it, try to do it again if I can. Yeah, it's going to start increasing, and here this is going to be the amount of increase. Maybe, well, actually, this is not a very good representation. Is I think it should be something like this. Here, this seems to be like that, and there seems to be another increase here, and maybe then decrease. Yeah, I think this is a better function whose, when you integrate it, it's going to correspond to this. All right, one very important point, since the cumulative distribution function is the integral of probability density function, and note that in discrete distributions we went from probability mass function to cumulative probability function. This was the natural route, we may say. When it comes to continuous random variables, yes, this may be also a route from the probability density function to cumulative distribution function, but we are going to see at least in one case, and let me give you the hint, it's going to be the exponential distribution, where we are going to see. First, we are going to be deriving the cumulative distribution function. From this one, we are going to go to probability density function. So the relation is integrate. So the inverse of integration is going to be the derivation here. So when you take the derivative of the cumulative distribution function, but note that the derivative condition that fx is continuous should be applicable, right? Then you obtain the probability density function. Well, the only, maybe it's a subtlety here, but still it's important, especially for those who are much more mathematically oriented. Fx should be continuous. So if you have an Fx such as this one, for instance, here like that, then Fx something like this. If this is your cumulative distribution function, note that at this point, this part will not be continuous, because up to this point here, actually, let me put it that way, there's going to be something like this, or either, or ups, or maybe here this value is not defined. We are going to have this one. So actually you can see that there is a discontinuity at this point, because the left hand side and the right hand side and the left hand side and the actual value are not equal to each other at this point. Therefore, there is not going to be a derivative here. Therefore, you cannot find the probability density function. But other than that, if you have nice functions, smooth functions like those, you can take the derivative and convert it to probability density function. All right, now next is going to be an example. Let's see, let me get rid of these. Yes, this one, yes, I'm pretty much learning. So let's say that we are given a probability density function 2 times exponential minus 2x, and x is greater than 0. Note that also the domain of, or the support of x is also given. First of all, let's show that whether that person who has given us this question, indeed fx is a probability density function, because, well, somebody has given it to you, but we cannot make sure that it's a probability density function. And how can we make sure that it's a probability density function? Actually, what we should do is we should go back and check the properties. Well, the properties, this last one is basically a definition. So actually, these two properties should hold. And this says that, the first one says that over all values of on real axis, there should be a non-negative probability. And the second part says that the probability density function should integrate over all values in real axis. It should be equal to 1. So let's see whether these conditions are satisfied. All right. So maybe showing it on a figure is going to help. So x greater than 0 up to this point, here we have 0. And from this point on, it's going to be an exponential decay, such as this one. It's never going to be exactly 0, but it's going to go to 0. So basically, it is this function here. Note that there's a discontinuity here, but we only define the function for values of 0, for values of x greater than 0, so it doesn't cause any problem. Anyway, so it is everywhere the probability density function, or let's just concentrate on the region where x is defined from 0 to, let's do it that way, x from 0 to plus infinity. So in this region, actually, this is fx is greater equals 0. So the first condition is satisfied. Now the second condition, integral of this from 0 to plus infinity to exponential minus 2x dx should be equal to 1. And well, actually, maybe I should skip the arithmetics here, or let me just do it. So it's going to be 2 and, well, okay, let me not be lazy and write all the intermediate steps. And it is 2 over minus 2 exponential minus 2x from 0 to plus infinity. I've done it right. This is going to be equal to this part minus 1 times exponential. As this goes to infinity, 1 over exponential infinity goes to 0 minus, and then you put 0 here, is going to be equal to 1. So this whole thing is going to be equal to 1. Therefore, the probability density function satisfies the given function satisfies the probability density function properties. All right, okay. So the second question, what is the probability that x is going to be between these two values? Now, when you are dealing with probability density functions, you should realize you are going to, and maybe even you have realized that since integration is usually the typical operation that we are going to use, these figures or graphs is going to be even more handy compared to probability the discrete distribution. So basically what it says is between 1 and 2.5, how much mass reside, or in terms of probability, that was the physics interpretation, how much probability is there, because the whole area corresponds to 1 here. Note that we have found the area just beneath this curve. So the probability 1 corresponds to the area here. So the area at this point is going to correspond to the probability that x is between 1 and 2.5. Note that equal to signs are optional, but usually we use it. Anyway, then it's going to, I'm going to do this part fast because it's a little bit boring in terms of simple algebra. So you just take the integral and the result is skipping those intermediate steps, 0.229. And the last question is, what is the probability that x is going to be exactly equal to 1? Please do not put 1 in the probability density function, and do not say it's going to be equal to 2 minus 2, because this is the value of the probability density function when x is equal to 1. The probability is different. At a single point for continuous random variables, we don't have the probability, therefore this is going to be equal to 0, not this quantity. Oops, let's also get rid of this one. Yes. Okay, now we are following the same route that we have followed in probability discrete random variables. Once we have defined probability mass function and cumulative distribution function in discrete random variables, we continued with some measures which can summarize the whole distribution. And those were actually mean and variance. And mean is expected value, and variance is what we call sigma square. Remember, in discrete random variables, we use this formulation. Weighting of x, position of each x with respect to its probability mass function. So the same logic follows here. Instead of this summation, we are going to be using an integral. Of course, when you use an integral, there's going to be also at the x here, if I can, right? And this is going to be between minus and plus infinity, or over domain of x. So this is probability density function that expected value of x you are going to be using pretty much commonly. And there's a very similar approach here. When it comes to variance, it's going to be simply in terms of when it comes to discrete random variable, remember that it was like this, right? Of course, weighted with respect to probability mass function. So it's the same thing here. Instead of this quantity, we put an integral and we put dx, and therefore we obtain this result. And note that previously, when this were summation, I think in bonus materials I've shown you that actually I even forget what I did yesterday. So it was x squared minus, I'm sorry, x minus mu square. And I have also shown you that variance here, so this is variance of x in discrete random variables, and this is also equal to expected x square minus mu square, which is basically equal to expected x minus mu square. I have actually shown the proof of this in bonus material. So the very same approach actually is also applicable here. Once in proving this relation, I haven't assumed, no, I have assumed, yes, of course, I have assumed a discrete random variable because I use a summation sign. Here, using the integral form, you can also show that this relation holds. And when this relation holds, of course, you can write the whole variance expression also in this form. So you can find the expected value of x squared by multiplying x squared by the probability density function integrating over all domain of x minus mu square. So it's the very same thing. This is left as an exercise for you. Please do it. the same logic is applied, but instead of summation sign, then we are going to be using integral. It's the same story. And the standard deviation is going to be, of course, square root of variance. No big deal. Well, there's another there's another analogy with the discrete case. For a continuous random variable, if we are going to find the expected value of a function of a random variable, remember we had a function of a random variable such as this one, then the expected value of that quantity were equal to this function multiplied by the corresponding probability mass function. So here the same thing applies. This one is changed into an integral. We multiply probability density function and integrate over domain. All right, now a question. Let's say that as a rich person, and here's Bill Gates, it may be anyone that you like, is waiting for his plane to be fixed. There's a problem with this plane. And time of waiting, and let's call this random variable with t, is known to be distributed. And how this is known, maybe due to prior experience, or those planes are known to be at that much of waiting time to be fixed. It is shown with this expression. So here, this lowercase t corresponds to the values of the values taken by the random variable t, which is time of waiting. This probability density function is some alpha constant that we do not know, divided by t cubed. And here, this t is the waiting time. And the domain is also of t is also given. Note that with the probability density function, the domain is also, it doesn't need to be always all the real axis. It is between, so now we have a bounded infinite set between 1 and 2 hours. And the question is this, let's see, oops, so you're, I think this one, nope, this is not this one. I should have used the mouse. All right. The question is, what is the expected time of waiting? And here, this should make a pretty much nice sense. So if you were Bill Gates, what would be the time that you expect your plane to be fixed? That would exactly be correspond to expected time, and also variance of this waiting time and the standard deviation of waiting time. Let's see. Well, usually, as I said, the best way to approach these problems is discrete continuous distribution is try to plot the probability density function if you can, at least for the time being. So this is going to be between 1 and 2, if you like, put 0, 0 here to show the significance level here. And the quantity that we are obtaining is here, this one. Well, this may be difficult to show you what this looks like, but note that as t increases, the probability density function will decrease. So it's going to be something like here is not defined. So I'm going to put dash lines, but here this is defined, and here again dash lines. Because here and here we have this is not defined. So actually we are talking about this region here. So this is our probability density function. So first of all, note that this probability density function is not all the parameters here given. This is unknown. Can we find this? Yes, just using the second property of probability density functions. The integral of probability density function over domain of x should be equal to 1. So it's going to be between 1 and 2 alpha over t cubed dt should be equal to 1. Actually, this is a slightly longer integral, and I'm not going to, again, I'm going to skip the integral. Please do it yourself, and please try to do it correctly, because if you just solve this alpha incorrectly, the rest of the question will be totally incorrect. Alpha is going to be equal to 8 over 2. Now let's just write the whole probability density function. It's going to be 8 over 3 divided by t cubed. And note that t is going to be, again, it's not sufficient to write the probability density function of this random variable. T is going to be between t. So this is the total representation of the waiting time for Bill Gates' plane. All right, we should continue with expected value of t. Expected value of t is simply going to be t ft dt over the domain of x, which is going to be equal to from 1 to 2. So now actually this is going to be equal to t times 8 over 3 t to the power 3 dt from 1 to 2. And again, I'm going to skip these points. If you did, I'm just going to write one intermediate step. Let me copy from my notes. It's going to be 1 over t from 1 to t. So you should obtain an intermediate result such as this one. And after a couple of more steps, we obtain 1.33 hours. Now, some in exam questions, sometimes, of course, same as the question is not asked, but questions such as these ones, for instance, if I have found in an exam 2.33 hours, should I have continued with doing the calculations? Actually, no, there are some very quick ways to check whether that you may be on the correct correct path. Now, your result, note that should be always between 1 and 2 hours. Because actually the expected time, since all the possible time values are between 1 and 2, therefore the expected time should be between 1 and 2 hours. And there is more than that. Note that the heavier part of the probability density function actually leans upon this side to 1 hour. So it is more likely that it's not going to be 1.5 hours, it's going to be less than 1.5 hours. If this were just a rectangle, something like this, and assume that this is a rectangle, although it doesn't seem to be a rectangle, then we would have said that actually I'm going to show you this is going to be called uniform distribution, but probably your heuristic says that here this should be the middle point, 1.5 is the expected value, and indeed it is. But here this part is more, the density here is higher compared to densities here, so that the waiting time should lean upon more to 1 hour. So this seems to be, of course, it's not a proof, but at least this seems to be okay. And variance of t is going to be equal to this representation here is much more easy to handle than t squared times 8 over 3 t cubed dt minus expected t squared. This is a more easy representation, and instead of this one you can write 1.33 square, which is this result. So there is one integral here. There is going to be, we are going to have 2t to the power minus 1 dt minus 1.33 square. And of course, again, skipping a couple of steps, it's going to be ln t. Please go over your notes about integral if you have forgotten how to take the integral of 1 over t. I'm sorry, this is going to be minus. And after a couple of steps, we end up with 0.076 hours square. Note that I always write the unit because I am an engineer. Anyway, as I said earlier, this is hours square, so the meaning is not very much clear. So an easier way of thinking about this, to find the standard deviation, take the square root of this quantity, and the result is going to be 2.6, or let's put it just this way, 0.26 hours. Now we have 27 hours, I'm sorry. Now we have a nice view about what's going on here. Actually, by the way, this is of course not a very nice representation. When we change it to minutes, it's not going to be over 100, but that's not the idea here. So the average waiting time is 1.3, and the standard deviation is something like 0.3. So the probability of having the plane working as early as 1 hour should not come to be a very big surprise for the rich guy, and maybe extending of that time to 6 hours also shouldn't be too much surprising. But maybe up to 2 hours, it may be a little bit surprising. Actually, can you find the exact probabilities? Yes, you can. Actually, the second part of the question is, the second part of the question is something about else, so I should talk about that. For instance, if I were to ask what is the probability that the fixing time of the plane exceeds 1.95, then you should have found here this area where this point corresponds to 1.95. You should have integrated from 1.95 to 2 with that probability density function, 8 over 3 over t cubed dt. And when you compute this integral, this result would correspond to what is the probability that the fixing time will exceed 1.95. So you can find the exact values, but just using these two numbers, note that, remember why we usually compute mean and variance. Instead of the probability density function, can we have a more handy summary? Well, of course, that's not the whole idea, but let's say that do we have a more easy to understand summary of the distribution? And in this case, as I said, it seems to have such a meaning. All right, now let me get rid of these, and the next one. Yes. While waiting, Bill Gates is losing money, represented by the function HT is equal to this one, $1 million, or whatever the unit. I'm not going to talk about the unit, is not important. What is the expected money he's likely to lose? I'm sorry. So the idea is very simple. We have a deterministic function of t, which is actually itself a random variable. Therefore, the amount of money that he's going to lose is also going to be a random variable. That's that much easy. So basically, what we are going to write is very simply expected value of HT is the quantity that we are interested in. And it's basically going to be HT here is going to be multiplied by ft dt. Note that it's subtlety, but here ht turns into a lowercase t because here is going to take a specific value. And integral is going to be between 1 and 2. And what we are going to do is actually we write t minus 1 square, and alpha was 8 over 3 over t cubed dt, if you do everything correctly. Now again, well, this is even a longer integral, therefore I'm going to leave it to you. And if you do all the operations, let me try to find where it leads to. Okay, this leads to 5.45, whatever the money is. So this is the expected amount of money. Now, some of you in previous midterm exams and final exams, I remember things like that. Wouldn't this be equal to, for instance, expected value of HT? I'm sorry. Wouldn't this be equal to all right, let me write that way. H expected value of T. So is this equal to this? What do I mean by that? Usually students, those who do this operation do not think about that, but they prefer directly writing 30 times what was the value that we have found here? It is 1.33 minus 1 square. And actually what they do without realizing is they use expected value of t here. So basically what they do is they put inside H the expected value of t. Note that these are not equal to each other. Expected value of HT would not be equal to H of expected, unless H and E can be changed locations, and this is possible only if H is a linear function. If there were no square here, yes, that would work, but please don't do this. But since there is square here, this won't work. So I hope the idea is clear. All right.